Hey there, and welcome to this explainer. If you're a grade 8 learner trying to lock down the real foundations of science, well, you're in exactly the right place. Today, we're taking a really fun, unhurried journey into the microscopic world. We're going to become atomic detectives, uncovering the invisible structures that literally make up everything in our entire universe. Seriously, take a second right now and just look around you. Look at a glass of water, the cell phone on your desk, the air you're breathing, or even just your own hand. What is all of this actually made of? In science, we just call all this stuff matter. But if you take that matter and zoom in way past what a regular microscope can even see, you eventually hit the ultimate building blocks of the universe. Okay, let's dive into this. Here is our quick roadmap for today's lesson. First up, we'll define the atom. Then, we'll meet the tiny particles inside it, crack the code on atomic and mass numbers, learn how to calculate those particles ourselves, and wrap up with some special atomic variations called isotopes and ions. Sounds good? All right, part 1. What exactly is an atom? The tiny foundation of everything. So this is the foundational concept for all of chemistry, and honestly, getting this unlocks how the whole physical world works. By definition, an atom is the smallest unit of an element that still keeps the chemical properties of that element. Now, thousands of years ago, there was this Greek philosopher named Democritus, and he coined the term atomos, which means indivisible. He figured if you kept cutting a piece of matter in half over and over, you'd eventually get a speck so incredibly small it just couldn't be cut anymore. For a long time, scientists were like, yeah, that makes sense. But modern science has actually shown us that the atom is made of even smaller pieces, called subatomic particles, and they're arranged in a very specific way. To really wrap your head around just how strange an atom's structure is, I want you to picture a massive football stadium. Thanks to some famous experiments, like Ernest Rutherford's gold foil test, we know that an atom is mostly just empty space. Right at the very center is this tiny, dense core we call the nucleus. If the whole atom were that massive stadium, the nucleus would literally be the size of a single little marble sitting right on the 50-yard line. And crazy enough, that tiny marble holds almost all of the atom's weight, while the rest of the stadium is just vast, empty space where incredibly small particles zip around. Moving on to part 2, let's meet the subatomic particles. These are basically the characters inside the atom. So, what exactly is packed inside that marble, and what's flying around the rest of the stadium? Well, let's meet our 3 main characters. To keep these straight in your head, I absolutely love using this simple little memory trick. First, we have the proton. Notice they both start with the letter P, so proton equals positive. Easy, right? Next up is the neutron. Neutron equals neutral. It has absolutely zero charge, just blank. And finally, the electron. You can think of the E as standing for extremely light and negatively charged. When we compare these 3 directly, protons and neutrons are really doing the heavy lifting here. They both weigh about 1 atomic mass unit, and they both live tightly packed together right in that central nucleus. The electrons, on the other hand, have a -1 charge and are almost completely massless. Get this, it takes about 1836 electrons just to equal the weight of 1 single proton. Because they're so ridiculously light, they don't live in the nucleus. Instead, they whiz around in the outer edges, in what we call electron clouds. Part 3, atomic and mass numbers. This is where we get into the mathematical rules of the atom. Now that we know the characters, how do scientists actually categorize them? Well, the absolute crucial point is this. The atomic number is simply the number of protons in the nucleus. Why does that matter so much? Because the number of protons is the ultimate identity maker for an element. It's literally an atom's fingerprint. If an atom has exactly 1 proton, it's hydrogen. End of story. If it has 6 protons, it's carbon. If you magically somehow added 2 more protons to make it 8, well, it isn't carbon anymore. It just became oxygen. So the protons tell you exactly what element you're dealing with. Now the mass number, that just tells us how heavy the atom is. Since we already learned that those tiny zooming electrons weigh practically nothing at all, we just completely ignore them when we're calculating mass. We only care about that heavy nucleus. So the mass number is really simple. It's just the total number of protons plus the number of neutrons. Which brings us nicely to part 4, calculating your particles. It's time to become a particle detective. With those definitions in our toolkit, it's time to put on our detective hats. See, if you look at a standard periodic table, it usually won't directly tell you how many neutrons an atom has. You kind of have to uncover that secret yourself using the clues provided. But don't worry, here is the foolproof formula for cracking the case. Step 1, look at the element and find its atomic number. Remember, this instantly gives you your number of protons. Step 2, find the overall mass number. Step 3, just do a tiny bit of subtraction. Take that heavier mass number, subtract the atomic number, and whatever is left over, that has to be your neutrons. Let's actually practice this together with sodium. So sodium has a mass number of 23 and an atomic number of 11. Step 1, the atomic number is 11, which means we have exactly 11 protons. Step 2, the mass number is 23. Step 3, we just subtract the 11 protons from the total mass of 23. Well, 23 minus 11 leaves us with exactly 12. So, boom, our detective work tells us that sodium has exactly 12 neutrons in its nucleus. All right, moving to part 5, isotopes, the heavy twins, same element, different weights. You know, science always has a fascinating twist, right? We just established that the number of protons can never change without changing the element itself. But what about those neutrons? That is exactly what brings us to isotopes. An isotope is basically a version of an atom that has the exact same number of protons, but a different number of neutrons. Because the neutrons are changing, the overall weight, or the mass number, of the atom goes up or down too. But because the protons stayed exactly the same, its identity hasn't changed one bit. It's really just like having twins, where one is just a little heavier than the other. Let's take a look at carbon, for example. In all 3 rows here, you'll see exactly 6 protons. That 6 guarantees it is absolutely carbon. But look at the neutrons column. Most carbon naturally has 6 neutrons, giving it a mass of 12. We just call that carbon-12. But sometimes a carbon atom naturally ends up with 7 neutrons, making it carbon-13. And sometimes it even has 8, making it carbon-14. Carbon-14 is actually really cool. It's a radioactive isotope, and scientists use its specific weight to carbon date ancient fossils and artifacts. It's still carbon, just a heavier version. And finally, part 6, ions, the charged atoms. This is all about gaining or losing electrons. So for this last part, let's look at the very outermost layer of the atom. We know protons are securely locked away in the nucleus, but those tiny, fast-moving electrons out in the shell, they can actually jump ship or even invite new stray electrons on board. When they do that, we get ions. Now, in a normal, perfectly balanced atom, the positive protons and the negative electrons completely cancel each other out. Like if I have 10 positives and 10 negatives, my overall charge is just 0. But if an atom gains or loses an electron, that perfect balance is ruined. The atom now carries an actual electrical charge, and we officially call it an ion. So this creates 2 very distinct types of ions. Think about it. If an atom loses one of its negative electrons, it now has more positive protons than negative electrons. This makes it a positively charged ion, which we call a cation. On the flip side, if an atom manages to grab an extra negative electron, the negatives win the tug of war. The atom becomes a negatively charged ion, and we call that an anion. And you know, this isn't just textbook theory. This electron swapping is happening right inside your kitchen. A sodium atom often loses an electron, which makes it a positive cation. Meanwhile, a chlorine atom absolutely loves to gain an electron, making it a negative anion. And since opposites attract, that positive sodium and negative chlorine lock together super tightly. The result? Sodium chloride. That's literally the everyday table salt you sprinkle on your French fries. It is quite literally an electric connection. Okay, as we wrap things up today, I want you to mentally highlight these 3 golden rules of the atom. Seriously, burn these into your memory. Protons define the identity. They tell you exactly what the element is. Neutrons define the weight. They tell you which isotope you're looking at. And electrons dictate the behavior. They tell you how charged the atom is. If you can remember these 3 specific rules, you have successfully mastered the basic architecture of matter. But before you go, I want to leave you with a quick thought experiment just to stretch your brain a bit before your next science class. We learned earlier that the atom is like a giant football stadium where almost all of it is completely empty space, right? So if the atoms making up your desk and the atoms making up your own hands are 99.9% empty space, why does the table feel so incredibly solid when you hit it? Why don't your hands just pass right through it? Think back to those negatively charged electron clouds zooming around the outside of the atom, and ask yourself what happens when 2 negative charges get way too close to each other. Keep exploring, keep asking questions, and we'll see you in the next explainer.